right, here are the objectives. Here's the definition. If you want to write it down. There we go. Let's talk about this. So we're not going to use a formal. We're actually not going to use a formal formula for this. So the idea is that once you've already drawn a queen, right? There's one less from the deck, and there are 4 kings left, right? So then this, right? This is our desired outcomes, right? Which are 4 kings that are in the deck left, and then over here, these are our total outcomes, our total possibilities. Why is it 51? Because, a king is missing. All right. All right, so we've got what's called a two-way table. Called the two-way table because you can read it both ways, right? You can read it horizontally, and you can read it vertically. And you can make different, you can find different probabilities or different proportions regarding this population, depending on which way you look at it. You can also look at it both ways at once, right? So this is a perfect way to get some conditional probabilities, right? And let's talk about this table real quick. If I was to want to know the probability of all these people, right? Someone had a high IQ and they had a gene present, right? And I would be looking at 33 over 102, right? But we're being asked to find the probability that a child has a high IQ given that they have the gene, right? So that actually is going to look more like 37 over 72 because we're only looking at people that have the gene present. Right? So this probability then is going to be, so probability, we're going to say probability IQ given gene is going to be equal to 33 over 72. Okay, and so here's just another picture of what I just did. All right. So let's do another one, okay? Let's find the probability that a child does not have this gene. All right? Probability that a child does not have the gene. So how many people have the gene? 72, right? Now we're not doing anything, no kind of, like they do not have the gene given they have a normal IQ or a high IQ or something like that, right? It's just straight up. What's the probability that they do not have the gene? So that would be out of the total, right? But what I just circled, 72 over 102, right? That's the probability that they do have the gene. So what do I have to do? I have to take the complement. I'm going to have to subtract it from 1. So I can take probability that they have the gene, which is 72 over 102, which I'm going to calculate. That's approximately 0.07. I guess we'll just round it to this. So then the probability that they don't, right, or the complement, right, is going to be equal to 1 let's talk about the next one. This is number 1. Let's look at number 2. What's the probability that a child does not have the gene given that the child has a normal IQ? Alright, so we're looking at given the child has a normal IQ. That's going to be our total possible outcomes, right? We're only looking at kids that have a normal IQ. We're not going to consider any other ones, the ones that have a high IQ, right? So that's the only group we're looking at. And what's the probability that they do not have the gene, given that the child has a normal IQ? Well, here's our not having the gene. So the probability that they do not have the gene, given the child has a normal IQ, so we're going to say normal IQ. That is going to be equal to 11 over 50, which is approximately, putting the start thing down. 11 divided by 50, or 22. Here we're going to look at independent events. They're events. The occurrence of one of the events does not affect the probability of the occurrence of another, right? So, the previous one that we did, those two events were not independent. Like thinking back to the cards, right? The probability that I pull a king, given that I've pulled the queen, is going to be different, right? As soon as I pull the queen, if I don't put it back, I've changed the next probability, right? So the first event actually changed the probability of the second event. If that happens, those two events are not independent. Another word for that is mutually exclusive. Right? So yeah, so you might have heard that term mutually exclusive. It gets used not with things that aren't probability, right? And I don't think I said that expressly. What does this little line mean? It means given, right? So you would say this thing as the probability of B given A. Two things that are mutually exclusive. Yeah, well, so, I was going to say, can it be raining and sunny? Yes, it can, right? There are no things that are both a cat and a dog, right? So the probability that you're a cat is mutually exclusive of the probability that you're a dog, right? If you were to pick all animals, right, out, right? If you were to pick a dog first, right, it wouldn't change your probability of picking a cat. Because those two things are separate. Does that make sense? And I say mutually exclusive a lot, right? And that also means independent. So you have to apologize. My vocabulary that I use for this is to say mutually exclusive. But independent is the same thing. So these formulas are important. They'll help you in the future. And actually, a common thing to do is to give you some numbers, right? And based on those numbers and using this formula, be able to tell if two events are independent or not. And I think we'll learn into that. All right, let's decide whether these events are independent or dependent. So if we were to select a king from a standard deck, so that's probability A, not replacing it, and then select a queen from the deck B, right? So it's a probability that I select a queen given I've already selected a king. This is definitely dependent, right? Why is it dependent? Because the second I pull, right, so if I pull a queen out, right, I've already changed the probability of getting a king. Because there's one less out of my total. And so that's what's going to make it a dependent probability. Now, if I was to replace it, then those two events would become independent. So if I pulled to see if I got a queen, then I put it back, then pulled to see if I got a king. Now I haven't affected the probability on the next side. Let's check out another example. Hey, let's decide whether these events are independent or dependent. So if you toss a coin, you get it, and roll, it lands on heads, and then you roll a six-sided die and you get a 6. Does the fact that I get a head or a tail on this affect what number I get? No, and that's how you would know that these two events are independent. All right, hey, let's classify these events as independent or dependent. Let's decide whether, yeah, it says again. Okay, so smoking a pack of cigarettes per day and developing emphysema, a chronic lung disease. Little public service announcement for you. I mean, do you think that the probability of getting emphysema is increased by smoking cigarettes? Then the two are related, right? Which means that they are dependent, right? Your probability of getting lung disease is going to depend on how much you smoke, or whether or not you smoke. All right. Let's look at another one. Exercising frequently and having a 4.0 grade point average. Now, while the two might be related, and you might actually, if you were to graph people's exercise time as, like, if you were to make a scatter plot of it and look at people's exercise time versus GPA, you might find some sort of relationship there. But does it mean that GPA, or maybe not? Maybe people that have high GPA don't exercise. I feel that as we get older, driven people tend to. I don't know. There might actually not be a relationship. So, with that said, right, it's kind of all over the place. I don't think that exercising is going to influence my 4.0 grade point average, right? Otherwise, I could just work out a lot and my grades would be great. I wouldn't have to do anything else. Well, my grades. Your grades. So these things are going to be independent. And I think that's all right. The multiplication rule. All right, it tells us that we can find a probability by multiplying the probability that A occurs times the probability that B occurs, given A occurs as well, right? That's what that says, okay? I just said that in human words. And this is for events that are dependent, okay? If your events are independent, it's much easier. All you have to do is multiply the probability of one thing times the probability of the other, right? So, for instance, rolling a die and then flipping a coin, right? You would be able to simply multiply those two probabilities in order to find, say, the probability that you flip heads and then roll a 3, right? You would use that. You would use this one for that particular situation. And then for the situation involving the cards, right, where we were to pull a queen and then find the probability that we pull a king, given that we pulled the queen, we would use this particular one. Okay, hey, so we got 2 cards selected without replacing the first card from the standard deck. Find the probability of selecting a king and then selecting a queen. So we know that these guys are dependent, right? These are dependent. So that means dependent. So that means that I have to use this formula, right? The probability A and B is equal to the probability of A times the probability of B given A. So, probability A and B is equal to the probability of A times the probability of B given A. Make sure I wrote that down. Cool. All right, so if we're going to say the probability A is that you get a king, probability B is that you get a queen. So what is the probability of drawing a sorry, we're looking at first probability of drawing a king, right? What's probability A? Probability of drawing a king. It is 4 out of 52, right? And now, what's the probability that you draw a queen, given that you've already drawn a queen? Well, sorry, a queen, given that you've already drawn a queen. So there are still 4 queens left, right? But now you got a smaller deck because there's 1 card missing. We can just straight up calculate that. We'll do 4 divided by 52 times, well, I almost put divided, times 4 divided by 51. I came up with a really small probability, which is 0.006. So very, very simple. Okay, we'll be able to wrap this up tomorrow.